right, so I'm going to talk today about some work I've been doing for a little while now on some Lagrangian pathways of warm circumpolar deep water on the Antarctic continental shelf with Matt England and Steve Rintoul. So just a very quick motivation here is we know that inflowing circumpolar deep water from offshore onto the Antarctic continental shelf is driving the ice shelf basal melt, and particularly accelerating in some regions around Antarctica, particularly the West Antarctic. Oh, I should update, this is no longer in revision, it's published. So Adele Morrison has done some work with a 1/10th degree MOM size configuration, which I'll talk about the model in a bit more detail in a minute, looking at the transport across the 1,000 meter isobath, so basically across the shelf break onto and off the Antarctic continental shelf. And what she showed here is, so on the right is showing the transport integrated around this 1,000 meter isobath, which is shown in the top left. And the green line is the dense shelf water flowing off the shelf. And then the orange line is the circumpolar deep water flowing onto the shelf. And what you see is that those are balanced locally. So the regions where you're having dense shelf water flowing off the continental shelf is actually where we're seeing the strongest circumpolar deep water flowing onshore. And that balance is actually true locally, not just sort of on a broader scale. So if you look, for example, in the Ross Sea, you can see a series of 3 troughs, and you see on the right here the green line showing that outflowing dense shelf water in the green, and the onshore flowing circumpolar deep water in the orange, and they're just offset slightly within those troughs. So this is a bit of a surprising result because it implies that the strongest CDW, so the warm water inflow, is actually happening in what we think of as cold shelf regions, the regions where there is dense shelf water formation. And that's not the same regions as where we tend to be seeing most warm water on the shelf driving the ice shelf melt. So I sort of wanted to think about you know, what happens to that water once it's on the shelf. And I can kind of think about 3 simple processes that control how much heat actually gets to the base of the ice shelf. The first is how much heat you have available in that reservoir offshore. The second is this transport across the shelf break that Adele was looking at. And then the third is the transformation of that water once it's on the shelf. So I wanted to look at this third step and look more at what happened with the hypothesis that in those cold regions, that water, you know, that warm water gets transported on, but has a short residence time and perhaps gets transformed very quickly and never actually makes it near the base of ice shelves. So this model is what I'm referring to as the MOM-01. It's a MOM size model, and it's slightly different from the 1/10th degree main Cosima model, and the difference being that it's forced with the core normal year forcing rather than the JRA 55 forcing. And it actually has different bathymetry, which I'll show in a little bit, that that's actually potentially problematic. And this is just showing the map shows the surface water mass transformation across the dense shelf water surface in the reds. So you can see that there's nice formation of dense shelf water in these coastal polynyas, which is great. And then the green is showing the bottom speed. So that's showing the overflow of the dense shelf water. And I have 10 years of daily averaged velocity output from this model run. And here's just a quick comparison of the temperature on the bottom of the shelf, on the left from the model mean, and then on the right from compilation of observations from Schmidt-Coe et al. It looks pretty good. There is some biases. The model seems a little too warm in the Eastern Ross Sea. this comparison's a bit difficult because the observations are very sparse, but it's generally looking pretty reasonable where we have observations. And so the experiment, the grinding experiment I've done is to release particles all around that 1,000-meter isobath. That's that orange line on the right, at full depth, and repeat that every 5 days for a whole annual cycle, and then track that forward for 5 years with the daily velocities. And I basically just follow the particles that are moving onto the shelf and ignore the ones that move offshore. And then I also track the TS and density along those trajectories. So this is showing, the colors here show the particle pathways on the shelf. So the yellower colors show where more particles go. And this is just for initially circumpolar deep water densities until they're transformed out. So as soon as particle leaves that density range, I'm not tracking its pathway anymore. So you can see it's the CDW on the shelf everywhere, except you can see that there's not really much getting far into parts of the Amundsen and Bellinghausen seas, and I'm going to talk about that a bit more. And then in the Ross and Waddell shelves, you see that CDW sort of circulates around partway and then it kind of peters out, and that's basically where it's getting transformed into denser waters. This here is showing the sort of age on the shelf. So it's basically the mean time since release of the particles averaged in each little lat long grid box. So you see there's a big range. There's some regions where the average time since release is only about a month, and then other places where it's 2 years. And so particularly you see these long times since release, these long ages of CDW along the edge of the West Antarctic. And you also see the longer time scales far into the Ross and Waddell shelves as that water circulates around quite a long pathway from the shelf break. And then it's quite variable in the East Antarctic. You do see a lot of these regional regions where the CDW seems to hang out for a longer time on the west side of a sort of basin, and then shorter time on the other side. Just another way to look at this is like a residence time, which is instead independent of where the particles first get on the shelf. This is instead the average time they spend in each lat long bin. And you see similar sort of patterns with longer time scales, like over 2 months in a small lat long grid box in the Amundsen Sea, versus quite short through these canyons in the Ross and Waddell shelves. So I was really curious why I don't seem to have CDW circulating very far into the Amundsen and Bellinghausen seas in some regions. So hopefully this movie will work. This is showing, I don't know if you can see the movie, but this is animation of particles in the Amundsen Sea colored by temperature. So the blue ones are near freezing and the red ones are warmer CDW. And you see, it looks like it's kind of gotten stuck now, that video, but you can see in the more western side of the Amundsen Sea, you see these intrusions of that warm water coming right into the coast. Whereas if you look in Pine Island Bay, you see some of these cold particles coming through, but you don't see a lot of warm water getting in there. And a lot of it's getting stuck kind of near the edge of the shelf. Yeah, movie doesn't seem to be going any further, but that's okay. And so I looked a bit more at the model biases here. So this is in the Amundsen and Bellinghausen, the model temperature, shelf bottom temperature minus the observed. And you see we've got this general warm bias in the Amundsen, but in this Pine Island Bay channel, you see that it's a slight cool bias. which suggests the model's not getting as much warm water in there as it as observed. And then in the Bellingshausen, you similarly have a kind of cool bias from over much of the region. And so I just yesterday had a look at the topography here, and it seems like in this earlier run that I've been using, the topography is perhaps part of the reason for the fact that you're not getting enough warm water in at least the Amundsen Sea. So the left is from the MOM 01 configuration I've been using, and the right is from a regional MIT GCM model. And so that's perhaps playing a role in inhibiting that CDW access. The good news though is if I look at the RYF 9091 simulation at topography, which is the same topography then used, I think, for all the other 1/10th degree Cosima simulations, it looks heaps better. So I'm starting to look at the shelf in more detail from these runs and thinking about redoing the experiments in this configuration with the better topography, and just doing a bit more comparison and how much better the shelf properties look in this run. Haven't been keeping track of time, but just one final thing that I've been looking at is looking at the water mass evolution on the shelf, and the way that okay, that's my bell, is it? Okay. The way that I've broken this down is to use different shelf regimes based on the Thompson et al. Definitions. And basically you have warm shelf regions where CDW has direct access to the shelf, dense shelf regions where you have dense shelf water overflowing off the shelf, and you can have CDW above that, and then a fresh shelf, which is where the CDW density incrops into the seafloor, and so there's no direct access. And just briefly, if I look at this breakdown in the model, and you see how each of these panels is showing how the particles evolve in the different water masses while they're on the shelf. And you see in the warm shelf regions, there's very little transformation. The CDW is basically preserved. The fresh, you see a little bit of transformation into lighter waters, but not a lot. But in the dense and cool shelf regions, you see rapidly that the CDW that comes onto the shelf is rapidly transformed mostly into denser shelf waters in a few months' time. So as I'm out of time here, I'll just quickly summarize and say that results show that this step 3, this transformation on the shelf, really limits the CDW access to ice shelves in the dense shelf regions, even when there's strong transport of CDW across the shelf break. And CDW therefore has a short residence time in these regions, but there's a lot of highly localized spatial patterns. And I'll just say that ongoing work at the moment is to look at the seasonality, and I'm also looking at variability in response to different forcings, for example, in the IAF run and SAMX runs, and also, you know, trying to diagnose a bit better some of these model biases and how well the model's doing on the shelf circulation. Okay, thanks.